Last time we just started talking about stress and torsion, and that's what we're going to go into today. So stress due to torsion. And so if you have a member like this, and you apply a couple like this to this end and opposite to the other end. So where does this stress come from? What type of stress is it? Well, if you think about what would happen, think about the deformation, not the stress first. So if you have a line that before the deformation does this, okay, say you paint that line on there. What's that line going to do after this deformation, assuming that this material can deform a little bit? So it's going to, yeah, so we're applying a couple this way to this end, this way to this end. So if you say this point stays at the same place, that line's going to angle down, okay? And so something that starts out as that's originally a the projection of this thing is a rectangle. After the deformation, it's going to be deformed like that. Okay. So this is where the shear strain comes from. So after the deformation, this is going to be something like that, right? And so you can think of it as a rectangle going to a parallelogram. Okay, so that's a shear strain. Okay, so that comes from the torsion. And what do we know about the relationship between stress and strain when you're talking about shears? You know that if we're talking about normal stresses and axial forces, you have a Poisson's effect. But there's nothing like that with the shears. So if you have, so Poisson's effect just says if you start out with something like this and say you stretch it horizontally, it elongates in the direction that you're stretching it, and it compresses on the off axis. There's nothing like that with shear. So whatever element of shear strain you have, that's the element of shear stress you have. You know, the values are going to be different, but like if you have, in this case, this would be that would be an XY. This is undergoing a negative XY shear strain, okay? The shear stress that goes along with that is an XY shear stress, a negative XY shear stress, okay? And so if you think about this mechanism, that's kind of all you need to understand to know where this shear comes from. Doing the calculations can get a little, they can get you turned backwards a little bit, but this is all that's happening. And what about something on the top? Well, the same thing is happening on the top. You know, if you painted a line along the top, did this deformation, the right side would come out towards us, the left side would go back, you get a deformation of that rectangular shape, and so you get a corresponding shear stress for that too. And so now for the calculations, so we'll do calculations of this shear stress for two types of cross sections. The first one is circular cross sections, and that's going to include solid cross sections and hollow, you know, like with a circular hole running down it. So that's pretty restrictive, only circular cross sections. And then the second thing we're going to do is thin-walled cross sections, thin-walled closed cross sections. And for these, we'll be able to do, you know, triangular, rectangular, all these different things. So we have a little more flexibility here, but the restriction is that it has to be just a thin-walled hollow shape. So I'm going to start by talking about circular cross sections. The magnitude of the shear stress is equal to the torque T times a value rho, I'll tell you what all these mean in a second, divided by a moment of inertia, and this is a new moment of inertia, I sub p. So capital T in this case is the torque. Rho is the distance from the desired point to the center of the cross section. And I sub p is called the polar moment of inertia. And you calculate this as, it's an integral definition. So it's the integral over the cross-sectional area of rho squared dA. So this is the cross-sectional area. So something to notice here is this integral definition holds for any cross-sectional shape. So the integral definition holds for any cross-sectional shape. But we're only going to use it for circles, so we can just come up with a formula for it. And this polar moment of inertia does have meaning for non-circular cross sections. It's just for us, we're only going to do it with circular shapes. And we're not going to use the polar moment of inertia for thin-walled shapes. We'll only use it for circles. Okay, so let's use this integral definition. So let me say, so we'll derive the formula we'll use instead of that integral definition. Okay, so first, think about a solid circular cross-section. And let's say that we have a radius r. We know that the definition is the integral over the entire area of rho squared. This rho is the distance from the center to whatever point you're looking at, dA. And so if we're trying to figure out a way to represent this integral, what's the element of area that seems most useful to use here? What is it? dr d what? dr d theta. rd theta. So the theta would be what? A pi slice. That's a good idea. I'm not going to do it that way, though. So the way I'm going to do it is like this. So here's my element of area. Okay. So this ring with an infinitesimal thickness so this distance is rho, and the area of this ring, so this thing is our dA, and that's equal to, you can think of stretching that. This is something that comes up in using integral definitions like this a lot, so it's a nice little trick for circles to get used to. We're going to take that ring, rip it at one point, and flatten it out into a long, skinny rectangle. Okay? So what's the thickness of that rectangle? dr, yep, so there's our increment. And what's the width of the rectangle? 2 pi r, it's the circumference of the circle. Okay? So dA is equal to 2 pi r dr. Oh, yes. Thank you. I'm using two different variables here. Yep. Okay, so this is, stretch it out into a strip. Then this thickness is d rho, and this length is 2 pi rho. Okay, so then I sub p is equal to the integral. What are the boundaries of the integral? 0 to r, yep, of rho squared times 2 pi rho d rho. And so you get the integral from 0 to r of 2 pi rho to the third d rho. Do that integration and you get 2 pi rho to the fourth over 4 evaluated from 0 to r, and you get pi r to the fourth over 2. So for a solid circular cross-section, I sub p is equal to pi r to the fourth over 2. Okay, so what would we have to change to apply this to a hollow circle? That's all you have to change. Yep, that's right. So now if you think about a hollow circular cross-section, from the center to here, we'll call that R inner, and then from the center to out here, we'll call that R outer. And the only thing we have to change is the integral is now from R inner to R outer. We're still integrating 2 pi rho to the third d rho. And if you do that integration, you get pi over 2 times R outer to the fourth minus R inner to the fourth. Okay, so for a hollow circular cross-section, IP is equal to pi over 2 times R outer to the fourth minus R inner to the fourth. Yeah.
What's the famous IP? For the other one, it's just resistance. Okay. What about what's this one IP?
Okay, what does it represent? Yeah. So the polar moment of inertia tells you how the area is. So again, just like for bending, you know, a shape resists bending more if more of the area is spread far from the neutral axis. Okay, that's what the aerial moment of inertia says. The polar moment of inertia says an object, sort of for the same reason, resists torsion more if more of its area is spread far from the center. So if you had two shapes with the same amount of area, one was a circular shape solid like this, and one was a hollow circular shape, you know, with a thin and say you had the same amount of material in both of these, the one on the right is going to be a lot better at resisting torsion. Okay, so now let's think about So let's think about a problem. Okay, so let's say that we have a circular cross-section attached to the wall. Our coordinate system's like this. Question? And let's say that we have a torsion on this side of 40,000 Newton meters. And let's say that the cross section is circular with a radius of 0.05 meters. Let's calculate the, so we're going to calculate the stress tensor due to this torsion here and up at the top. And so if you're looking at it from the z-axis, so now you have to do a little sort of mental manipulation, you know, three-dimensional thinking. With this coordinate system, what direction is the z-axis pointing? It's coming straight out at us, yeah, straight out of the page. And so in this view, so say that this view is what somebody sees who's over here. Okay? So for this view, the x-axis is coming straight out. The y-axis is up. And the z-axis is this way. And so this dot, say this is going to be part A, that's right here on the cross section. And this dot at the top that's going to be part B is up here. So there's A and there's B. Yep.
You're very good at drawing on this.
Ah, thank you.
Mine is much creepier.
That's good too. Really, the key thing is just conveying what direction it's coming from more than the artistic beauty here.
Will we regrade it on?
A little bit, but not much.
Put it
Yeah.
on the final?
Yeah. The final is mostly drawing. Okay, so if you think about, so what's going on with this, first of all? So 40,000 Newton meters acting to the right on the right side. What's happening over here on the left side? It's a couple. Can anyone, and it is equal and opposite, can anybody sort of express why? I mean, I think a lot of people would have had this intuition, but if you had to calculate that, how would you do it? Like, how would you know that, like, I didn't tell you that there's a 40,000 Newton meter couple over here on the left. How do we know that that this really is in torsion? Yeah, right. So what it really is if you think about it as an equilibrium problem in 3 dimensions, then you would get this from the rotational Newton's second law about the x-axis. Okay, if you wrote those 2 equations, you'd have plus 40,000 here, plus m is equal to 0. So m has to be equal to negative 40,000, and so that gives you this. Okay, so you can do that from Newton's laws. All right, well, let's first think about that point A. We know that the shear at that point A is equal to the amount of torsion times rho over IP. Which of these values do we know? We do know the torsion. And again, if you're not convinced that you know that there's a torsion of 40,000 at this point, yep,
You can find IP very easily because we know the dimensions of the cross-section.
that's right. Yep. So we'll just plug 0.05 into that formula for IP. But I was going to say, so if you can't eyeball this and say, like, right at this line, like, how do we know that there's a torsion of 40,000 at this line? Because that's what we care about, right? I mean, how do we know it's not torsion of 0 here and increases to 40,000 or something? Exactly. You could do those cuts and think about the X rotational equation the same way that you would to figure out that this was a couple of negative 40,000. Okay, so I sub P is equal to pi times 0.05 to the 4th over 2. And I think you get a value of 9.82 times 10 to the minus 6. The units are meters to the 4th. What's the rho value? It is the radius. Would you ever have a problem where rho wasn't the radius? You could, if we were trying to calculate what exactly. If we were trying to figure out what the stress was at a point that wasn't on the outside edge. Okay, yep. So rho in this case is equal to 0.05. The torsion is equal to 40,000. And so the magnitude of this shear stress, and in a way this is the easy part of these problems, is just finding these values and plugging them in to get the magnitude of the shear stress. The magnitude of the shear stress is, so 40,000 times 0.05 divided by 9.82 times 10 to the minus 6, and you get a value of 2.04 times 10 to the 8. And what are the units? Newtons per meter squared, pascals. Yep. So now the last thing we have to do, and the part that gets trickier, is we have to think about both what element of shear this is, and we have to think about what the sign of it is. So now there are two things to figure out geometrically. First is, what element of shear is it? And second, what's the sign? And the way to do that is to, at whatever point you're looking at, so think of that point A. Think of a rectangle surrounding your desired point. And how it will deform, just like that little, you know, set of pictures I gave you at the start, okay? If our coordinate system is like this, so we're looking at it from the side, and that point A then is here, okay? Then imagine a rectangle. What's going to happen after this deformation takes place? So we're talking about a torsion this way on that end and a torsion this way on that end. So what's going to happen to that rectangle? Which side's going to go up and which side's going to go down? The left is up, yep. And so since this element is this, you know, what element of the shear stress is non-zero in this deformation? It's on the, you can think of it as, this is caused by a shear stress that's on the positive x face in the negative y direction, right? You have to have something like that and that, okay? And then you have these two, but those don't matter to us. So this says that the shear stress that you calculated is the xy stress. And since we have on the positive x face a stress in the negative y direction, that has to be a negative 2.04 times 10 to the 8th. Any questions about that? Yep.
I'm not seeing how it deforms like that.
Okay. So that's sort of what I was trying to get at with this. So if you had like a rubber bar of this shape, you know, and you drew a little rectangle on the front, right where A is, and then twisted this side this way and this side this way, that rectangle would take a shape like this.
Sure, okay.
So that's the way you have to think about it. Think of doing it to like a rubber bar or something.
Sure.
And what's that rectangle going to do?
This side we're twisting upside down.
That's right.
Bring it up.
Yep.
I see it.
But notice that, you know, what's going to happen to the rectangle depends on where on the shape you're looking, you know. Like if you're looking at a rectangle that's painted on the back of this thing, say this is see-through and you're looking at a rectangle painted on the back, then this side is going to go up and that side is going to go down. You know, so you have to sort of think of it in 3 dimensions each time.
Would it also not change much? That deformation of that rectangle would not be the same if it was closer to one side or the other.
That's right, but that row takes care of that in the calculation, right?
Rho is distance from the center of the, sort of the central axis.
Oh, you mean if it's closer to one of these two ends?
Yeah.
It wouldn't be as far down. It wouldn't be translated as far down, but the shape would be the same.
Yeah.
So it would be this rectangle, but just closer to the line. Yeah, the shape would be the same. It just wouldn't be translated as much. Okay, so finally we can say that the stress tensor due to this torsion at that point A is equal to 0, negative 2.04 times 10 to the 8, 0. Then because of the symmetry of the stress tensor, negative 2.04 times 10 to the 8, 0, 0, and all zeros in the last row. Okay, so now the next one gets a little bit harder, part B. So now if you think about this deformation, the equivalent of that rectangle I just drew is like, this is the side of it. Okay? So like if we want to see that rectangle face on, you know, this is the coordinate system, x, y. If we want to look at it from up above, I'm just doing this so I can see Dan draw I again. Then that rectangle is going to be, and actually, let's not do it that way exactly. It's more like, well, let me just draw the coordinate system and you can sort of orient yourself. So let's say that we're going to look at a rectangle where this is the x-axis, the y-axis is out towards us, and the z-axis is down. Okay? So if I was going to draw the person like before, these would be the person's feet. There'd be crotch shot. There'd be the back of the person's head. Okay. Okay, you follow that drawing? Stop looking at that picture, you perverts. Okay, so now remember that the torsion is like this and like this. So what's that rectangle going to do under this deformation? Which side's going to go up and which side's going to go down? Yeah, the way I drew it here, it's going to be the same as before. But now these sides refer to different axes, right? So now the fact that this is going down means that's on the x face in the positive z direction. Follow me? You can see how this can get sort of tricky, you know, like you have to do this kind of thinking with every one of these problems. So this is on the x face in the positive z direction. So in this case, the shear xz is equal to positive 2.04 times 10 to the 8. And the stress tensor at the point B is equal to 0, 0, 2.04 times 10 to the 8, 0, 0, 0, 2.04 times 10 to the 8, 0, 0. Okay? It can't get any harder than that, right? Well, so what's going to happen is what about this? So Now what about points that aren't, let's say, on the coordinate system axes? Okay. So like, for example, in this cross section, if X is coming out towards us, Y is up, Z is this way, what if we wanted to calculate the stress at this point, where, say, this angle was 30 degrees or something?
Just treat it as a projection into those axes.
No, you can't do that because it's not a vector. Yes, so that's what we're going to have to do. We're going to have to use a coordinate system. So we're going to start by using a coordinate system that's rotated in a way that we can calculate it like we just did. Okay, so call that capital Y, call this capital Z. Then once you find that stress tensor, then you use the tensor rotation to go back to our desired coordinate system. Okay? Does everyone follow what I'm talking about, just in principle? Okay, so the approach is, whoops, we're going to calculate the stress tensor in a coordinate system that's rotated to make the calculation possible, I guess. And then we'll use Q times that stress tensor times Q transpose to express it in the original coordinate system. Okay, so for this one, say that it's the same problem. We're just trying to calculate the stress tensor at this point. In the capital, the red coordinate axes, what stress element and what sign would we have in those capital axes? Well, so we'd be looking at it like this. So there's capital X, there's capital Y. And it would go from this to this. So we know that we're going to have a stress in the X, Y element of negative 2.04 times 10 to the 8. So the stress, anybody want me to slow down on that, or you follow what so I'm just doing it the same way I did before, except I'm doing it in these capital coordinate axes. And so our stress tensor in this capital XYZ coordinate system is 0, negative 2.04 times 10 to the 8, 0, negative 2.04 times 10 to the 8, 0, 0, 0, 0, 0. And now what rotation matrix do we have to use? So we're trying to rotate from the red to the black. Yep, so it's the x-axis is the one we want. And is it a positive or negative rotation about the x-axis? Well, we want to go from the red the x-axis is this way. So, you know, a positive rotation would be like that, so it's going to be negative third. So theta would be equal to negative 30 degrees. And then our stress tensor would be Q times the one we just calculated times Q transpose. Oops. Okay, and you know, I don't have time to do it right now. We'll do some of this next time. But the interesting thing here is in this coordinate system, all we had is shear stresses, right? All that torsion does is produce shear stresses. When we do this transformation, we're going to get normal and shear stresses. So when you do these rotations, shears and normals, they're not really fundamentally different things. You'll go back and forth between one and the other. Any questions? Okay.